let X be any set, and suppose you have a family of sigma algebras. So let's suppose you have, and it could be any number of them. It doesn't have to even be a countable family. So let's say, let me write a nice A here. Let's say A sub alpha, script A sub alpha, over alpha in J, I guess maybe it's more conventional to use curly braces in this situation. So suppose this is a family of sigma algebras on X. Okay, so it's a collection of it's a collection of collections of subsets of X. Then, if you intersect all of them, if you intersect these collections of subsets of X, if you intersect these collections of subsets of X, then that is a sigma algebra. So a really terrible way to state what I'm trying to say here is sigma algebras are closed under intersection. A specific sigma algebra has to be closed in intersection, because that was part of the definition. But that's not what I'm talking about here. Here I'm saying the collection of all sigma algebras on X is a collection which is itself closed under intersection. If you intersect sigma algebras, an arbitrary number of sigma algebras of any cardinality, then that will be a sigma algebra. So how do we see that this is true? Well, let's just talk through the requirements. So let me go back to the definition of sigma algebra, the nice tight definition that we had here. So to be a sigma algebra, for this to be a sigma algebra on X, it needs to contain X. So it needs to contain X. That's property 1. Does it contain X? Well, each of these is a sigma algebra on X, so they all contain X. So their intersection contains X. Right? For something to be an intersection, it has to be in all of them. Property 2, if I have a sequence of things in my alleged sigma algebra, then the union of that sequence has to be in the alleged sigma algebra. So say I have a sequence of things in here, then each of those things in the sequence is in each of these individual sigma algebras. So maybe that's worth writing. If we have a sequence in there, then each AN is in each of these for all n and for all alpha. So here J is meant to be an arbitrary index set. It doesn't have to be, it could be finite, it could be countably infinite, or it could be beyond uncountable. Okay, so this is what we have. When we say this is a sequence in there, we're saying each one of these is in there, which means, and in there means it's in each one of these. Then, for each fixed alpha and J, the intersection, or the union of the ANs is in there, is in A sub alpha. That's because A sub alpha is a sigma algebra, so it's closed under countable union. So these ANs individually are in A sub alpha, and so their union is. And what I've stated here is what is needed to have the countable union be in this intersection. So since this object here is in A sub alpha for all alpha in J, I can conclude that this object here is in the intersection. Okay, so I don't want to finish writing that. It's pretty simple. It's all just a lot of notation, basically. And what else? There's one more condition to check. Closure under complements. So if I take some element of this, I need to show that its complement is in this. Well, if I take an element of this, then it's in all of these. These are sigma algebras, so its complement is in all of them. And if its complement is in all of these, then it's in this. So I start with some A in here. Then A is in each of these. So A complement is in each of these. So A complement is in this whole thing. That's all. So that was justification for saying that this is a sigma algebra on X. Oh, and by the way, I should say here J is non-empty, just so I don't have to think about how to handle an intersection over an empty index set. Now, let X be any set, and let's say F, script F, is some collection of subsets of X. So I'm not assuming it's an algebra of sets or a sigma algebra. Then we define, sorry, I want to start with the notation. We denote by sigma of this thing the smallest sigma algebra on X that contains script F. So this is like the sigma algebra on X that is generated by F. So here's a way to explicitly describe it, kind of explicitly, not very explicitly. You can take this to be our definition, is that it is going to be an intersection of all the sigma algebras on X that contain F. So let's say it's an intersection of sigma algebras running over all sigma algebras on X such that they contain within them F. So we call this the sigma algebra on X that is generated by F. So I'm telling you on the one hand that we can define it like this, but I'm also using a descriptive name that seems to imply some things about it, namely this phrase here, the smallest sigma algebra on X that contains F. So there is something to kind of prove here. Is the notation that I'm defining here really describable by this phrase? Is it really the smallest sigma algebra on X that contains F? Well, first of all, is it a sigma algebra on X? Yes, because it is an intersection of sigma algebras. And we just argued that an intersection of sigma algebras is a sigma algebra. And it is a non-empty intersection, not over an empty index set, because there definitely exists some sigma algebras on X that contain F, For example, the power set of X itself is a sigma algebra on X that contains F. So that justifies part of this phrase. So let me go through the different elements of this phrase. The smallest sigma algebra on X that contains F. Okay, so here's the point that I want to address. Is this thing that I defined, where I intersect all the sigma algebras that contain F, is that really describable by this phrase? It is the smallest sigma algebra on X that contains F? Now, I have just justified at least this part that it is a sigma algebra on X. So that's good. It is a sigma algebra on X because it is an intersection of sigma algebras on X. And there are other things to justify. Does it contain F? Definitely it contains F, because it is an intersection of sets that contain F, right? Okay, I'll consider that to be clear. So it contains F. How about smallest, and how about the? So those are the other parts of the phrase that I want to justify. Is it smallest? So smallest means if you have a sigma algebra on X that contains F, then it contains this one as a subset. That's what it means to say this one is the smallest one. That is to say, if you have any other one, then it contains this one as a subset. So say you have another one. Say B is a sigma algebra on X that contains F. Let me just write that in a shorter way. And F is contained in B. So this is how I write script B. So this is supposed to look like a scripty letter in the same way that these A's look like scripty letters. I would write a Roman B more like this. So that's the difference. Okay, so say script B is a sigma algebra on X that contains F. Then this one, which the notation is that this is, I'm writing for short, I'm writing this, sigma of F. That's the sigma algebra generated by F. If B is a sigma algebra on X that contains F, then B is one of the things that I'm intersecting here, right? B is one of these things. So if I take an intersection of a bunch of things, then that intersection is a subset of any one of the things. So this definitely contains this thing, which is an intersection of a bunch of things, one of which is this. Okay, so that justifies smallest. And finally, the. Well, if you had something else that satisfied all of the properties I'm describing here, that was a smallest sigma algebra on X that contains F, then so let me recycle this notation here. Suppose B is also a smallest sigma algebra on X that contains F. Then we still have this inclusion, that the construction here, this intersection construction, is a subset of B, because B is one of the things that's being intersected here. But also, since B is the smallest, and since this is a sigma algebra on X that contains F, we also have this inclusion then. Right, to say B is a smallest sigma algebra is to say that it is contained in any other sigma algebra on X that contains F. So this is an example of a sigma algebra on X that contains F. So B is inside it. So you get both inclusions, and that means you have equality. And that's the uniqueness. That's why I say the. There's only one. So the stuff I'm describing here, by the way, is definition 1.2.5. and also proposition 1.2.6. I sort of merged those, and that's what we're discussing here. So this is kind of similar. So what we're seeing is an example of a thing that is generated by another thing. So how to describe this? We're looking at sigma algebra generated by something that might not be a sigma algebra. It means the smallest sigma algebra that contains that thing. So another example of that is, I'm trying to pick something that's probably familiar to everyone, is if you have a subset of a vector space, so let's say V is a vector space over the reals or whatever. Let's say V is a vector space, and you have a subset, might not be a subspace, but you can talk about the subspace it generates. And there's some notation for that, rather than using sigma like we were doing over there. Maybe you use angle brackets or something like that. And the subspace it generates is something you can describe in a few different ways. You could say it's the smallest subspace of V that contains S. That's one way to describe it. Another way to describe it is you could say it's the intersection of all subspaces of V that contain S. So the intersection of W over all W, a subspace of V, let me use this less than or equal to symbol for subspace, such that S is a subset of W. So that's another way to describe it. And yet a third way to describe it is to say it's the span of S, sometimes it's also called span, in the sense of it's the set of linear combinations of elements of S, finite linear combinations. So like C1, S1 plus C2, S2, etc., Cn, Sn, running over all. It could be any size finite linear combination, and any coefficients here in whatever is the field, and any vectors in S. So you have these kind of three descriptions. One reason, so these two descriptions are very intimately tied logically. It works pretty much because the intersection of subspaces, an intersection of subspaces is always a subspace. So the collection of subspaces of V is closed under intersection. This is analogous to how we just argued that an intersection of sigma algebras on X is a sigma algebra on X. The collection of sigma algebras on X is closed under intersection. This is the same, in the same way, that fact allowed us to get an analogous connection between these two ways of describing sigma algebra generated by a family of sets. But for it, in linear algebra, you have this nice other way of describing things, this third thing here, which tells you explicitly what are the elements of the set, right? Take all linear combinations, that's what it is. So these on their own are pretty difficult to imagine what they are until you come up with a nice constructive description like this that says here's exactly what are the elements of the set. So it would be nice if we could do the same thing here for our definition of the sigma algebra on X generated by a family of subsets of X. It would be nice if we could go from this abstract description as the intersection of all the sigma algebras that contain that set, or the smallest sigma algebra that contains that set, to something that says here's exactly what they are, rather than, so here's another way of putting it, this way of saying things is like starting with everything and then cutting down until, whittling away until you only have what you want. And this way, on the other hand, is like building up out of nothing, right? Saying, here are the things I'm going to include, the linear combinations. So can we do something like what I've circled here, but for this? It's not going to work so well, but we'll try anyway, and just think about it.